Hi, I'm Darren and welcome to Level Up EE Lab. I finished all the work I intended to do on my FE149 meter, and the results, well, some good, some bad. Let's check it out. It is a good day here in Level Up EE Lab because I've got this FE149 working again. Ta-da! If you remember in the prior episode here on DC Plus, the needle just went full to the left and just plain would not respond to input voltage, but now it's working. Now, what was wrong? Well, remember in the last episode that I measured the source voltages at all three FETs, and TR number 1, which is in the input circuit, was different than the other two. It measured around 3.2 volts from source to ground, whereas the other two were around 4.3 volts. And that clue started me on the path to check for electrically leaking capacitors or possibly drifted resistors, which are common suspects in old vintage gear like this. And those are easy, non-invasive, non-destructive tests to make. So following the schematic, I worked my way around TR1, and I got about halfway through the whole schematic and wasn't finding anything anomalous. No electrically leaking caps, no seriously drifted resistors. So I decided to move on and focus on the FETs. Now, there's a basic check that you can do on N-channel and P-channel JFETs for that matter. And you can use a DMM to make those measurements with the circuit powered off. There's two measurements. The first one is to check the gate to either the source or the gate to the drain with your DMM on diode mode, which is what you can use to check any silicon or germanium diode and look at that forward voltage drop. And then, of course, reverse the leads and make sure that it's not conducting in the other direction. Did that measurement, didn't see any problem there. The second measurement to make is to check the drain to source or source to drain resistance with the DMM on ohms mode. And for that, you should see a relatively low resistance, somewhere on the order of tens to a couple hundred ohms, again, depending on the model of JFET and just how low its resistance is. But before doing those tests, I did need to do something slightly destructive. I needed to remove these two guys here. This is CR12 and CR14. These are a pair of diode-connected 2N5172 NPN transistors that, according to the manual, are there to protect TR1 from overvoltage. And if I'd left these in place, I was convinced that their junctions were going to interfere with the measurements I was trying to make on TR1. So removing them solved that problem, but it also gave me a chance to check these out of circuit, because if these are supposed to protect TR1, are these still any good? Well, I checked both of them out using similar tests on the DMM. I didn't see anything wrong. There is a third mode on this particular model of DMM where you can check, where is it? Yeah, right here, the HFE of a transistor. I got erratic readings when I was measuring these. So, maybe these were bad, but that's secondary because what I found was TR1 is actually bad. And I'll put the data on screen here. You can see for all three of those JFETs, the 2N5163 JFETs, that I made those two measurements, and TR2 and TR3 have resistances that are much lower from drain to source or source to drain. They're around 140 ohms, whereas TR1 was much higher, over 2 kilo ohms. And all three checked out fine for the gate to source. But that big clue right there is that resistance value being so high. Unfortunately, I don't have spare 2N5163s or any JFETs for that matter laying around. So the thing that I could do, and it was temporary, was remove TR3 and put it in the spot for TR1. According to the manual, you don't need TR3 on DC or on ohms mode. It only works or comes into play on AC. And ta-da, that's what fixed the meter, again, temporarily. By doing that part swap, I can demonstrate that it's working. And in fact, it's actually giving me readings that are pretty close to being spot on, just over 9 volts, about 9.6 volts for a fresh 9-volt battery is pretty good. So that's the temporary fix. The permanent fix is I'm going to move on now to replace all three FETs with J112s. I did go on to EEVBlog, and there's an interesting thread that I started there, and I'll put the link to it with this video. And I do want to give a shout out to all the guys there who gave me great and excellent advice on how to proceed with trying to substitute a rare JFET, and it looks like the J112 is going to work fine. So that'll be the next thing I'm going to do is swap those in, and I'm also going to replace these two 2N5172s. These are actually available new even today, and there's absolutely no reason to keep these in here if they're suspect at all. I'm going to replace those as well. I bought 10 of the J112s with the intent to test them and choose the 3 closest to each other in performance. But is that strictly necessary for this meter? Well, I'm not sure. It is a differential amplifier after all, so conventional wisdom says yes, I should. Plus, the Sencore service manual states that whenever you order replacements from them for the original 2N5163s, you need to specify the color when ordering, which makes me think that maybe they were matched or at least binned in performance for some reason. But I'll never know for sure. But on the upside, doing a basic sort of JFETs is very easy. There are 2 parameters here that I'm interested in. The first is the gate to source cutoff voltage, or more commonly called the pinch-off voltage. And the second is the source to drain current with 0 voltage at the gate. In this application, the second one is of more interest, but I'll measure both parameters. Here's the setup that I'm using for measuring the pinch-off voltage. It is very simple. I'll throw a schematic on screen here, but essentially just connect the source to ground, the drain to a positive DC voltage source. In this case, I'm using 10 volts because that's the voltage in the unit, and then apply a negative DC bias to the gate, starting at negative 5 volts and then slowly increase towards 0 while you monitor the source to drain current. And that's what the Keithley over here is monitoring that voltage, and then the DMM right here is monitoring that current. I'm just going to adjust the 2718 here in the background until I see the current here approach about 1 microamp. That is the typical standard. If we look closer at the J112 datasheet, there's actually a large range specified for the pinch-off voltage, -1 to -5 volts, and that's pretty typical of a JFET. Their test voltage was 5 volts, but that doesn't matter here. I'm only looking for consistency among these 10 samples and just doing a relative comparison between all 10. So let me demonstrate how I did this for sample number 1. I'm at -4.1. Let me bring that closer to 0 and until we see the current come up on the DMM. Comes up pretty quickly. Very sensitive. This potentiometer is fairly coarse, but that doesn't really matter so much, as I'll explain here in a minute. And I'll call that close enough. So 3.311 volts. As it turns out, I don't need super precise voltage control on the gate voltage because of this wide range that these particular JFETs are going to have. I measure between -3.322 and -3.8 on all 10 of these samples. So I got a large range to work with here. So if I do want to sort by these values, I think this method is working just fine. Now let's look at the source to drain current with 0 gate voltage. If I measure it the way the datasheet specifies it, which would be with 15 volts across the drain and source, I'd get IDSS, or the saturation current. And look, this is yet another value with a wide range. In this case, it's 5 milliamps minimum. Could be 5, could be 10, could be whatever, I guess, on an individual JFET. I could even use the IDSS and pinch-off values to estimate the maximum transconductance of each JFET, but I don't think that's what I need here because in this application, the JFETs are working at a much lower current than 5 milliamps. Looking back at the schematic, there's about 6.8 K of resistance from source to ground on TR1 and TR3, and a bit more than that on TR2. And there's a quiescent voltage of 4.7 volts at their sources. So 4.7 volts over 6.8 K is about 70 microamps, not 5 milliamps. So a better idea would be to measure these J112s with a 6.8 K ohm resistor in the source to more closely simulate the actual application. And here's what that circuit looks like. I'll apply 10 volts to the drain, ground the gate, and then measure V sub S, which is the source voltage and is the voltage drop across that 6.8 K resistor, and then compare the results for all 10 FETs. So let me demonstrate that real quick for sample number 1. 2.954 volts, and that's all there is to it. And just like with the pinch-off voltage measurements, there is a noticeable range in the values from around 2.96 volts to about 3.43 volts. So here's the raw data from both measurements, and I'm also showing it sorted by V sub S and V sub GS and the sample-to-sample differences. Notice how the groupings are very similar between both measurements. Samples 1, 6, and 2 are near one end for both measurements, and samples 4, 7, and 3 are grouped at the other. Now, this is likely expected behavior for JFETs, I think, just based on how they work. I think there's close coupling between those two values. So I guess I'm going to go with samples 4, 3, and 7. They have the least amount of variation from each other and also happen to have the highest V sub S values, closest to the 4.7 volts shown on the schematic. I'm not sure if that's important or not, but I'll find out after I install these in the unit. Okay, I've finished installing the 3 J112s and the pair of 2N5172s, and drum roll please, it's working. Yay. Now, it is reading a bit high, actually a fair amount high. That's about 10 volts, but it's showing 13 volts. No big deal. I think that can be fixed by going through the calibration routine, especially by adjusting R10, which sets the meter gain. Now, soldering in those new transistors was a bit tricky. The circuit board construction is definitely from early on in the printed circuit industry, meaning it's only single-sided copper, and the copper is not bonded as well as it is today on typical FR4 material. It also didn't help that someone had replaced TR1 and TR2 at least once in the past, so a couple of the pads were already lifting off. So I had to bodge in those connections, but I think it's good enough to last a few more years. So on to the calibration. Let's see just how well I can dial it in. I've finished the DC and AC balance and DC and AC voltage range calibrations. Those were accomplished by adjusting trimmers R21, R22, R10, and R59. I used my Keithley right here as the master. That's good enough for calibrating an analog meter. For the DC range, I needed half a volt of DC. So I used my 2718 power supply with a roughly 10-to-1 resistor divider so I could improve the sensitivity of the adjustment. So rather than trying to set the controls on the 2718 to half a volt, I could set it to 5 volts and gain quite a bit of sensitivity adjustment there. The specs are plus or minus 1.5%, and I was able to adjust it to within that spec. However, there was a minor issue. It had to do with R10, the 500 ohm trimmer. I ran out of adjustment range. Now, I'm sure that's because the J112s that I used don't have the same transconductance curves as the original 2N5163s, so that was throwing off slightly the actual current flowing through the meter. No big deal, the fix was simple. I noticed resistor R5 that's in series with R10, it's 680 ohms, so I lifted one lead and started playing around with adding some additional series resistance, and I ended up adding an additional 1K, and that let me adjust R10 and get the DC range calibrated. A better fix would have been to replace R5 with a larger value trimmer, like 2K, let's say, but I don't have one, so I went with the parts that I have. I was concerned that it might throw off the linearity, but my measurements show that it did not. There might still be some effects on the thermal response because R27 and thermistor R4 are in parallel with R5, but I'll worry about that later. Moving on, for the AC range, I need half a volt RMS to calibrate that, so I used my recently repaired BK Precision 3020 function generator, set to about 100 Hertz. The specs here are larger, plus or minus 3%, and as it turns out, it was right on without needing any adjustment. But I did notice a strange thing happening around 60 Hertz. There's a strange oscillation. Let me see if I can replicate it here. Yep, you can see the needle bouncing back and forth on the FE149. So clearly, there's some kind of coupling happening here between the input of the FE149 and the mains frequency. It's not an interaction between these three instruments. I disconnected the Keithley, disconnected the Siglet, still does it. And it's not a problem with the power supply in the FE149. I checked and there's only about 300 millivolts of ripple, but that's before it's all absorbed by the Zener shunt regulator made up of ZR4 and R26. The DC downstream from there is very smooth. There's no noticeable ripple more than a few millivolts there. There's something happening here, but it'll take more poking around to see if I can find the cause. It's definitely not a high priority. I finished attempting the remaining calibration checks for DC and AC current and ohms. And before I did those steps, though, I replaced the existing 3-prong power cord socket with a modern style one. I did not have the original power cord, and this original socket uses an oddball footprint that's different even from the one used on the BK Precision function generator I showed a moment ago. So it made perfect sense to swap it out to the modern standard, and the modifications were super easy and they look neat and clean now on the unit. Unfortunately for DC current, bad news was found. The selector switch is malfunctioning. I've got this hooked up right now with the Keithley in series, and I'm trying to measure around 100 microamps, and you can see there's nothing on the display until I start fiddling with the push button, and then it comes to life. Yeah, it's not a cleanliness issue. I cleaned those without disassembling them, did the best I could to clean them with regular contact cleaner. I suspect the switches are just worn out, or even worse, because this is a current setting, there could actually be arc erosion that took out that switch. But unfortunately, it's probably a lost cause. AC current is more bad news. It plain just does not work. I took a close look at the manual and the circuit, and most of the circuit is shared with the AC volt measurement, and that works. Not going to troubleshoot it further right now. I rarely need to measure AC current anyway, and I don't want this thing to become a time sewer for me to suck up a whole bunch more time to troubleshoot it. It's just not worth it right now. On some bright side, the ohms mode does work, and it works about as well as you would expect for an old analog meter. So let me demonstrate that real quick. I'm going to use this same 33K resistor. Get my leads here disconnected. Make sure these aren't shorted out. All right, let's go to 10K and ohms. First, let's zero our meter at the zero end of the scale. Then double check it at the other end. That looks pretty good. I know the parallax is off for you guys. I have to turn this at an angle so you don't see my face or the camera or both when I'm recording this, so you're not seeing it straight on. But nonetheless, we can see here that we're getting, and that would be the red scale here, it's just over the 3 mark, and so that would be about 32K. So not bad. Again, you're not going to use an analog meter nowadays to measure ohms unless you have no other choice, but it's nice to know at least that it does work. So no grand slam home run today. I guess I'll have to settle for maybe a 2-run double. But that's how it goes sometimes on these projects. You just don't know what you're in for until you dive in and you find things that end up just compounding. And in my case, getting the DC voltage and the ohms function working, well, that's good enough that I'll have some use for it in the future. And who knows, when I get through some of the other projects on my list, I may pick this back up again and see if I can get those non-functioning functions to function again. At any rate, I hope you enjoyed this short series on this FE149. And as always, I hope you are enjoying the content here on my channel. So until next time, bye for now.